Good morning, everyone. I'm having a little trouble with the beamer this morning. At least you see the image now. It's a little yellowish, so I hope it will work. Yeah, don't really know much what to do about it. Good. So today we're going to talk about matrices and determinants, but first a little recap, like I very often do at the beginning. Recap to vectors. We talked about vectors when we defined vectors. We said that there are different notations for it. And then we talked about, we defined vectors as a set of scalar, an ordered set of scalar values, or a d-tuple. And of course in 2D it's a pair, in 3D it's a triple. And we call these individual scalar values coordinates, and the number of them is called the dimension. Now, the reason why I'm repeating this is that today we want to talk about matrices, and if you look at the definition of matrices, it's actually looks quite similar. We also have a matrix. A matrix is also defined by an ordered set of values, only in this case the values are not linearly ordered, but they are ordered or arranged in a grid, an array, or a matrix style. So we have a 2 cross 2 field of values, and we identify these values by their row and their column. Usually we write the row first and then the column second. So we say we have an m cross n matrix if the matrix has m rows and n columns, and we call this m cross m the dimension, in the same way as we called the value n the dimension for a vector. Only in this case the dimension is actually 2 values, because of course it's not only important how many scalar values we have, but also how we arrange them in a 2D way. And similarly to the vectors, where we called the individual values coordinates, we have we call the entries of the matrix usually the coefficients of the matrix, although depending on where you look in the literature you also find the term elements or entries for it. So this is a pretty simple, obvious definition of something that is then, again, will prove, like the vectors, to be a very valuable concept that we can use in graphics, or we use it in graphics a lot. And we use it a lot because it comes with a whole frame set of tools and arithmetics and characteristics that are very, very helpful in graphics, as you will see later. So, in similar to the vector case, you can imagine that there are a lot of special cases which at the beginning we just have to learn them and or introduce them and remember the names. Later on you will see why they are important and why they have special characteristics and in which situations they are useful. So first of all, we have the case where the dimension, where the number of rows is the same as the number of columns. So the dimension is not m cross n, but m cross m, or n cross n. So both of them have the same value, which is why this is called a square matrix, obviously, because if the number of rows and the numbers of columns are the same and you draw them equally, not like I did here on the slides, then it is a square. And if this square has 0 values everywhere except for the diagonal, so the aii coefficients are unequal, only the aii coefficients can be unequal to 0, then we call this a diagonal matrix. Again, the name, of course, comes from the fact that if you look at it and you have only zeros in this upper right and lower left triangle, then of course it's a diagonal. And you see here, by the way, these coefficients, aij, or the coefficients of the matrix are usually addressed and indexed by their row and their columns, and usually we write the row first and then the column second. So aij means the coefficient in row I and column j. Usually when we write matrices we start with 1, 1 and then go up to the dimension. Be careful with that, because for example for vector spaces we of course start with the origin with 0, so sometimes then we only go to a value less if we start counting by 0. Sometimes, depending on the source, you also see matrices starting with 0, but usually we start with 1. So be careful also with this in exams, that if it's not further specified, then we start with 1, because it can, of course, then if you have a formula that requires you to address a specific coordinate, and then you start to counting with 0 or with 1, you just get the wrong one. Good. Yeah, so if the diagonal is unequal 0, we call it a diagonal matrix. And then, of course, with these diagonal values these diagonal coefficients have special values. There are two other cases. One special case is that they are all 1. Then we call this the identity matrix, and we will see later very soon where the name identity matrix comes from, and it should be obvious where the name zero matrix comes from. That comes from the situation where all the values in the diagonal are 0, and then of course if the other values are also 0, we have only 0 values in this matrix. And we call this the zero matrix, or sometimes also the null matrix. So these are just some straightforward definitions of special types of matrices. And of course, similar to the vector, we also want to do some arithmetics with matrices, and this is for addition actually pretty similar, or almost identically defined to the vector case, where we just said we have two vectors that have the same dimension, and then we sum them up by just doing a pairwise addition of the matching coordinates. Here we add, of course, the coefficients of the matrices. So, for example, for this value A22, we add it with a value B22 if this is matrix A and this is matrix B. And then, of course, 11 plus 5 is 16. So the new matrix C at the entry C22 has the value 16. So this is really simple and very obvious way to define addition. Also, you see here that I use this notation here, which is very common, that matrices are generally denoted with uppercase letters in order to distinguish them from other variables. For example, scalar values, which are usually indicated with lowercase letters. And you also remember that for a vector, I usually draw this little arrow on top to indicate that it is a vector, although you also find different notations. Like we said in the book, they use boldface for that, for vectors, which I'm not using here because they're very hard to draw with. Boldface letters are very hard to draw with a pencil. Good. Yeah, and of course you also see here that this is only defined if the dimensions match, which is obvious. It's the same for vectors also, and for vectors we didn't even explicitly note it because it's obvious. You cannot add a two-dimensional with a three-dimensional vector. In the same way, you cannot add matrices that have different dimensions. So in this case, it is obvious, but we will see later a case where we have different conditions for the dimensions. So, subtraction, yeah, again, there is nothing much to say about this. It's defined in the same way as addition, only that we subtract the values. And then, of course, we also have the multiplication with a scalar value, which is similar to the vector case, where you had this, also the multiplication with a scalar value, where we then just multiply each coefficient of the matrix with this scalar value. So, for example, if we have the value 5 here, and we multiply it with the scalar value 2, then it becomes 10, and all other values, so for example, 1 becomes 2, all other values are also multiplied with the scalar value. So yeah, this is again a pretty simple and obvious definition. Now, for the vector case, we already had then the situation that when we came to multiplication of vectors, it was not that obvious how to define that. Of course, there is the obvious way to just multiply the coefficients individually, like we do also with addition, where we sum up the coefficients individually, but the result of that is something that is of no real value or no real interest. So a definition like this, although we could do it, doesn't really bring us any benefit. What does bring us a benefit, or has brought us a benefit in vector calculation, was, for example, the dot product, where we multiply two vectors and then get a scalar value. And in matrix multiplication, we also have a definition of multiplication of two matrices, which looks a little weird at first, but it is actually, if you understand it and look about what it means, it is actually quite simple. We have two matrices A and B, multiply them to get a matrix C. Now, and then we calculate each new coefficient of the matrix by making a sum over certain values of A and certain values of the matrix B. Now, if you look here, the sum here goes over the index k from k equals 1 to NA, which is the second dimension, or the number of columns of the first matrix. And then it takes an A in a certain position I, and the I doesn't change, only the K moves. And here for B, only the K moves and the J stays. Now I said the first index is the row, and the second index is the column. So this I indicates the row, and the J indicates the column. And for I, we see we go through one row with the index K. We stay in one row and move to all the columns. And with B, we stay in one column, and we move with this sum here over all rows. And then we multiply these coefficients pairwise with each other, and then we take the sum of these individual products. And that sounds very complicated now, but if you look at an example, it's actually quite obvious how we do it. This is our matrix A. This is our matrix B. And then we go for for Cij, we look for A in the eth row. So here E equals 2, because we want to calculate C22. For JB, we look in the jth column. So here J is also 2, so we look in this column. And then we multiply pairwise these coefficients with each other. And that way we get these products here. And then we sum them up. And then we get our result 5, which is the new entry C22. Now, that might look a little strange, but if you think about it, the calculation is actually exactly the same as the dot product of two vectors. So if you consider this here as a vector, this row and this column, the calculation here, the formula, is exactly the same as calculating the dot product of these two vectors, which also shows us what conditions have to be fulfilled that this is defined, because you see here these matrices do have different dimensions. Here I only have 2 rows, and here I have 4 rows. But these rows here, the number of columns in the first and the number of rows in the second match, which has to be, because otherwise I would have here a situation where there is no pair, where I do not have a corresponding A and B value to multiply with each other, so this formula wouldn't work. So we see here that these two dimensions, the second dimension of the first matrix, the number of columns, must match the number of rows of the second matrix. That is the condition that has to be fulfilled, but the other two conditions can be, the other two dimensions can be different, and they then later, of course, influence our result. So what we have here is a matrix from MA cross NA multiplied with MB cross NB. So this here must be NA, and the result is then MA cross NB. So this part is what has to be identical, and this part specifies what comes out of it. And what I found intuitive or easy way to do this on paper is to actually write it that way. Because if you write them in like this table style or cell style, bottom left first, up down, right the second one, then you can see, you can just go through them here. You multiply the coefficients pairwise with each other. Multiplication of all these pairs here. And then you sum up the result, and then you get your entry here at exactly that position where it appears in the final matrix. And that also nicely illustrates then that these two dimensions here have to match. So this has to be equal with that one. And it also nicely illustrates the result. This here and this here are then the resulting dimensions of, is the resulting dimension of the final result matrix. So you see here the formula looks a little difficult or not obvious at the beginning, but if you do the multiplication and you know how to do the procedure, it is actually quite simple. Good. Now this matrix multiplication has, of course, certain properties or certain characteristics. One of them is that it is distributive over addition. So if we have the sum of two matrices and then multiply it with another one, it's the same. We have the same result as if we multiply the matrix with the individual matrices and then take the sum. It is also associative, so it doesn't matter in which order we do the multiplication. If we multiply several matrices with each other, so for example, if we multiply three matrices, A, B, and C, we can first multiply A with B and then multiply C, or we can multiply B and C and then multiply A. But the most important thing is to remember that it is not commutative, so we cannot just change the order like we do with normal scalar multiplication, where we can say, I don't know, 2 times 3 is the same as 3 times 2. But a matrix A times B is not necessarily the same as a matrix B multiplied with a matrix A. And we can see, we can see this with a simple proof. If you want to make a proof of this statement, we just have to, because we say we cannot do this, or it's not always the case that this happens. It can, of course, be in individual cases happen, but in general, it is not the case, which is means that we can prove it by just showing one simple case, one simple example where it doesn't work. And I felt you see very random matrices 1, 2, 3, 4, and the other is 5, 6, 7, 8. And now if we multiply this, then we have here 5. We have here 14. Together this is 19 for the first coefficient. If we do it in reverse order, we have here 5 again, 5 times 1. 6 times 3 is 18. 5 plus 18 is 23. So we see already the first coefficient is different, so we don't even have to calculate the others. We have already shown that if we multiply AB, we do not get the same result as if we multiply B with A. So this is our proof. QED, by the way, stands for Quod errare demonstrandum. It's Latin, and mathematicians usually do this at the end of the proof, and it means this is what has to be shown. Actually, I don't know the English translation for it, but yeah. Good. Now we have matrix multiplication, and now if we look again at these special cases that we defined, of course the zero matrix is obvious. If we multiply a zero matrix with something else, we will always get as a result a zero matrix, because we multiply each coefficient with, or in each, we always have products here where there is one coefficient from the first matrix involved, and if this is 0, the result will obviously always be 0. And in this case, actually, it works both ways. If we multiply a zero matrix with a matrix, or if we multiply a matrix with a zero matrix, we always get the zero matrix. So this is one example where this switching of the order works, but it doesn't work in all cases, as we have shown here. Another example where it works is the identity matrix, where the matrix where we only have ones in the diagonal. And this is now the situation where you see why we call this the identity matrix, because if we multiply a matrix with the identity matrix, we always get the matrix that we are multiplying it with. And that is also obvious if you write it down. If you have the matrix here, and then, for example, for one row here, for one column here, you multiply that with one row here, and then you have a 1 here and only zeros at the other positions. And then, of course, this means that here only these are all multiplied with zeros, and only at this position here you have this the value from this matrix, which means that you have an identical copy. So this is 1 times CAIJ and 0 all the other values. So this is obvious that this only results in the original matrix. Good, so you see the zero matrix and the identity matrix are basically have the same characteristic as the 0 and the 1 in the scalar multiplication. Now, another special case of a matrix is this so-called transposed of a matrix, which is created from an original matrix by just mirroring their coefficients at the diagonal. So if we look at the diagonal here, and then the transposed matrix is just basically created by swapping the indices. So if this is the transposed, then at the position ji, we have the value that in the original matrix we have at the position ij. So it's basically just taking this value, exchanging it with that one, this one with that one, and then we get our transposed matrix. Now I have an example here. I mean, this is so simple we don't need an example, but the example is here to illustrate that, because here, although the dimensions are not the same because of how LaTeX has plotted it, it looks like they are both have the same dimensions. But of course, if you mirror them at the diagonal, this doesn't have to be the case. So if you have, for example, here a 2 cross 3 matrix, then the result is of course a 3 cross 2 matrix. You're mirroring still at the diagonal, but of course here is nothing to mirror, so you have this, you move this 6 to this position here, but here of course you don't have anything, so this is why the dimensions also are just swapped. Good. Now again, like all matrices and all special cases, they have certain characteristics, and one characteristic of the matrix, of the transposed matrix, which we will use later then also in a proof, is that if you take the product of two matrices and then create is transposed, you get the same result as if you take the transpose of the second one and then multiply it with the transpose of the first matrix, which is a statement that you can accept it, or you can say, well, I want to have a proof. So let's look at how we could prove that. First of all, let's look at the dimensions. If the left side is defined A multiplied with B, and then the transpose of that, the multiplication has to be defined. That means the dimensions of A and B have to match. For A, the second must be the first dimension of the, and the first dimension of B must be the same. So it must have the same value here. Now, if we, and then the result is, of course, if we take AB, that leads us to an MA cross NB matrix. Now, if we take the transpose, of course, the dimensions change the order. So we have then, for AB transposed, we have NB cross MA matrix. Now, for B, if you swap the dimensions here, and then you swap the dimensions here, then you see that this product of the matrices is defined, because then B transpose is the first one, so this new second value matches the new first value of A transposed, and the result is again MNB cross MA, so we have both have the same dimensions. So on the dimension side we're safe, but the question is, of course, how are the coefficients also the same? And to see that, let's first look at the left side of the equation. So we're looking at AB transposed. So first, if we think about how do we calculate the coefficients of a matrix, I called it C dash AB. So a new coefficient of that matrix, C star ij, not dash, C star, sorry. A new coefficient Cij is calculated by taking the row of the matrix A, so it's the matrix A, this is the matrix B, multiplied with the column of the matrix, with column J of the matrix B, and this is then our new coefficient Cij star. So that is just the definition of the matrix multiplication. Now, if we take the transpose of that, what we do is then we take, if we want to have a position Cij in our matrix, so this is the new matrix C, which is the transpose of this C star, then we just have to look up this value and write it here. Or if we want to calculate it directly, of course, if you think about what we do here, instead of if we calculate it directly, instead of calculating this one and looking it up, we could also calculate it directly, but then we just have to swap to use the different indices here, because if you want to have Cij, then we look up C star Ji, which is exactly the same here, only we write different index here, which basically means we're multiplying this row as a column now and this as a row now. But it's pretty obvious, of course, that this is just the definition of it, and then if we want to look up this value here, we have to write the indices here different. Good. Now if we look at the right side, B transposed, A transposed, so I also introduced some different notation here to illustrate the different cases. So A and B are the coefficients of the original matrices. Then I denoted A and B with an index T at top to illustrate the coefficients of the transposed matrices. And then we want to calculate this matrix, I called it D now, with the coefficients Dij at that is then the product of both the transpose in that order. Now, if you write that down, of course, what you do is you go through the row of B transpose, because that is your first one here, multiply that with the values in the column of the second one, which is A transposed here, and then you have your entry here. Now, if you think about what values are in here, let's just see why I have written this one here. If we create the transpose from A, the J row of A becomes the column J of A transposed. And the column I of matrix B becomes the row I of the transposed matrix. So if we want to have the row of the transposed matrix, we have to look it up in the column I of the original matrix. So we have to look it up here. And so let me just illustrate this. Fortunately, I cannot switch easily the colors here, which is why I'm making these weird signs here very often. I hope you are. It helps you and doesn't confuse you more, because it's like if you look at it later and then you see all arrows all over the place, it's kind of confusing. But here you see, we take here this B ki, so we run the index over the column here, over the column, which means we run the index over the rows here, but keep the column I, because this column I is the same as the row I in the B transposed, which is what we want here. So, and the same is for A. Instead of running over the column, we run over the row here now. And this is why, of course, we can write it also in this way. Now, if you look at this, is just a multiplication of two scalar values. So this is commutative, so we can also write it in that order. And if we write it in that order, then you see that these Dij are exactly the same as the Cij that we calculated on the left side. So we have seen on the left side and right side, we are calculating the very same thing. And since we have not chosen any concrete value, but chosen a generic value ij, this is through, generic value is ij. This is true for every coefficient in the matrix, which means we have proven the general case that this is always the case. And this is actually one of the reasons why I made this proof in a more detailed way, to illustrate these two differences of these two proofs that we had so far. I mean, there are a lot of statements in the course, in the lectures, that I just put there and I don't prove it. Usually I say then it's a good exercise for you to prove it yourself. In a couple of situations I make a proof, which is either because the proof is very important or because it illustrates a certain thing, like a certain concept or a certain approach. And I've chosen these two to prove these two, and you will have more in the tutorials. And I've chosen these two because they represent two types of proofs. The first one was a proof where we have shown that something doesn't work or is not true. And then, of course, we can take just one example and show that this is not true, and then we have proven that. So this is often called a proof by counterexample, because we say a statement is not true, and we prove that by showing just one case where it's not true, which is obviously then this is enough as a proof. But it's not enough as a proof to show an example or to show 2 or 3 or 100 or 1,000 or a million of examples for a general case, because even if we show a million cases that it is true, it might be very likely that it is true, but we cannot be 100% sure that with the 1,000,001th case it might not be true. So in a statement, in a situation where we want to show that something is true, we have to make a general case where we use general values, like I did in the previous case where I said I only use Cij to do all the calculation, and this ij can be any value in the matrix, so we have proven it for any possible value, and that is then a general proof that is required for such a situation. And I'm highlighting this so often because so often I see it in exams that people just bring a few examples to show a general case, and this is something where you cannot get any credit for. So be careful with that, you read it very carefully. What do I have to prove, and what is the appropriate way to prove it? Good. All right, so now the final special case of a matrix that we want to introduce now is a so-called inverse matrix, and the inverse matrix is defined as a matrix is called an inverse of another matrix if we multiply that matrix with it and then we get the identity matrix. So we note this with this index -1 on top, and then if we multiply A with the inverse A minus 1, then we get the identity matrix. And we see already, and this is another example where it is actually commutative, but be careful again, matrix multiplication in general is not, but in this case it works. So if we multiply a matrix with its inverse, we get the same result as if we multiply the inverse with the matrix, which is in both cases the identity matrix, because that's how the inverse matrix is defined, of course. But we also see by this, if we look at this equation, that this only works for square matrices, and it is not always possible to define an inverse matrix of another matrix. So if we have a matrix, there are situations where we cannot find another matrix that multiplied with that one will lead to the identity matrix. And we will see some examples, in fact, of this later that illustrate this also from a geometric interpretation. And in fact, these inverse matrices are very important in graphics, and we'll talk a lot about them later on, which is why I will not spend much time on them now, but I already mentioned graphics or the relation to graphics. Now, so far we just talked about matrices as a really abstract concept for calculation, but of course there is a relation to graphics, otherwise we wouldn't talk about it here. And the relation becomes quite clear if you look at the vectors that we introduced at the beginning, which is also why I had this initial slide at the beginning. If you remember, we actually, at the beginning I had this one slide where I showed you different notations for vectors. So for example, this V with an arrow on top or the boldface. But I also had this column or line representation where in the line we have these commas here, which are the ones that I use so far interchangeably, because the second one is of course easier to write if you are having a full text, if you write it in text, whereas the first one is probably a little more illustrative and better relation to graphics. But I never used this, never used this third one before, although I introduced it at the beginning, where we do not have commas here, but instead we have this T at top. And of course, if you, I hope you see the relation now. This T stands for transposed, and it kind of illustrates the idea that you can also look at vectors as the columns, or you can interpret the column of matrices as vectors, and then an n cross 1 matrix is exactly the same thing as a vector. And you see this, for example, for scalar multiplication or the dot product, which is again a nice illustration why the matrix, the calculation of one coefficient in matrix multiplication is actually the same as the dot product of two vectors. If you write it in that way, then the dot product is exactly the same as matrix multiplication. Only here, of course, we make the assumption that if we have a single value, or a matrix with a single value, we just omit the brackets. So this is more the notation of it. But from the actual calculation, you see that the vectors fit quite nicely into the matrix concept. So you could also see a vector as like a simplification of a matrix or a special case of a matrix, in contrast to what I did at the beginning when I started with the vector and then introduced the matrices basically as a 2D generalization of it. Good. And another case where this vector multiplication is very important is to multiply. Here is the example where we multiply a vector with another vector, so 2n cross n, an 1 cross n matrix with an n cross 1 matrix. Let's write down 1 cross n with n cross 1. But of course, you can also multiply a vector with another matrix as long as this dimension here is the same as the dimension of the vector. And the result is then this new vector here. But of course, if the number of rows here is different than the number of rows here, then of course this has a different number of rows. But if we use a square matrix here, that is, if we have the same dimension, if they have the same number of rows and the same number of columns, then the result is again a vector with the dimension d, with the same dimension as here. And this is exactly the case that is very important in graphics that we will use a lot in the next lecture, because you see we can use matrices to transform and vectors and to create new vectors from existing ones. But this is what we want to do next week. So this week we are focusing more on the other important aspect of matrices in graphics, which is linear equation systems. Now, a linear equation system is defined as, well, a system or a selection of linear equations. A linear equation is an equation where the variables are all to the power of 1, which is most often the case in what we do, because we're dealing with linear algebra here. And of course, the name linear algebra already suggests that we're mostly interested in linear stuff. But we have seen an example like the square quadratic equation, the formula to solve quadratic equations. But mostly we're dealing with linear equations here. So we have here linear variables x1 to xn, and multiply them with constant values, and then we get a result, which is then of course depending on the values of the variables here. And the question is then, what kind of values do fulfill for x1 to xn, fulfill one line and also all the others? So what is the solution of this linear equation system would be then a value for values for x1 to xn that fulfill all equations here. And this is now the relation to matrices is of course that we can write this in matrix, so-called matrix equation form, which is then just a vector Vx multiplied with a matrix of the coefficients here. So we basically take all the constant values and the variables and write them separately. And if you remember how matrix multiplication was defined, then you will see that this B here is exactly then the same as we get when we do it when you do it in this way. And this is then of course easy for the writing when we do the calculation of it, when we try to solve the equation system. But of course the question remains, why are we doing this in the first place, especially in a course about graphics? So what is the geometric interpretation of an equation system? To make it a little easier for you, I wrote it in that way. So any idea? Come on, you should know that. What does one line here represent if I write it that way? No one? Surface, yeah, close. It's a plane. That's the implicit equation of a plane. Yeah, the surface, yeah, that's you made it right. It's the implicit equation of a plane. You remember the normal vector? That's the AIs here. And then this 17 gives the orientation, the position of the plane in the space. So this is the implicit equation of the plane. This is the implicit equation of a plane, and this is the implicit equation of a plane. Now, we say the implicit equation of a plane, the solution to this equation are all points that are on this plane. Now, the solution to the second one is, of course, all the points that are on the second plane. The solution to the third one is all the points that are on the third plane. So the solution to all three of them are all points that are on all three planes, which means they are at the intersection of the three planes. So if we take this linear equation system and solve it, the result will be exactly the intersection points of the three planes in our 3D space. So if we think about what kind of intersections could we have, what would be possible solution to that, how could this solution set look like? Let's first look into what kind of solutions we get when we intersect two planes in a space, in a 3D space. Of course, those two planes could be identical. Then we have an infinite number of solutions, which is exactly the plane. We also have an infinite number of solutions if the planes intersect. Oops, in this way, because then the intersection is a line, which is also an infinite amount of values, so we also get an infinite number of solutions. Or the planes could, of course, be parallel. Then there are 0 solutions because there is no intersection between the two. And these are the only options that we have for 2 planes in a 3D space. Now, if we look into if we intersect 2 planes in a 3D space, now if we add a third plane to that, let's look at the left case first, that we have the 2 planes, the original 2 planes are identical. Of course, then if we add a third one, then we get exactly the same options. We can again have a case where they are all identical. We can again have the case where one of them is parallel to the other 2 identical ones, or they can intersect in a line. So these are exactly, of course, these 3 cases. Now, if we look at what happens in this case, if we add a third one here, it can, of course, be identical again to one of them. It can be intersect with them in this way, or it can also be parallel. So we get 3 more cases. It can be parallel. It can be parallel to 2 already parallel planes. It can be parallel to one of the original planes, or it can be identical, or it can go. No, this is the case. Yeah. Okay. Yeah. So we see we get these 3 new cases here. This here. And these are all the options that we have. Now, the interesting thing is, of course, what happens in this case if we add here another plane to it. Then, of course, this plane, that was the one I was looking for, this plane can really intersect directly in this original line here. So that is a new case. It can also intersect, this can also happen, of course. We already had that if we had 2 parallel cases, but of course this can also happen. It can also happen that it is, of course, identical to one of them, but it can also happen that we have 0 solutions by intersecting just in a way that the 3 intersections with the other planes are just lines that are all parallel to each other. Then, of course, we also don't have an intersection point. And, of course, it can happen that it intersects with this line, but only in one point. And this is actually probably the most common case. And this is exactly the case that we're interested in when we are solving linear equation system. Because if we solve this linear equation system and it has one solution only, then this solution is the point. So it means these planes must intersect in one specific point. Good. And we can do this with Gaussian elimination. Now I see it's already time for a break, so we do this after the break.